Right. Hello, everybody. Thank you very much for coming. This is the physics department colloquium, but this time it is joined with the APS because our speaker will be from the APS department. First, let me introduce the speaker. So today we are happy to welcome our own Stephen Cranmer from the APS department here. Stephen received his bachelor's degree in physics from Drexel University in 1990. And then PhD in physics and astronomy from the University of Delaware with working with Stan Owocki on outflows from rapidly rotating massive stars in 1996. And after that, he moved to the Harvard-Smithsonian Center for Astrophysics, where he worked for about 17 years as a staff scientist. While there, Stephen transitioned from general stellar physics, I guess, to solar physics, and was a team member on the ultraviolet coronagraph spectrometer instrument on the SOHO spacecraft. But in 2015, so almost 9 years ago, right, he came to CU Boulder and joined the faculty of the APS department, where he is now an associate professor. And Steve is currently serving as the associate chair for graduate studies at the APS department. He studies the hot expanding outer atmospheres of the sun and of other stars. And today he will be telling us about the turbulent origins of the sun's hot corona and the solar wind. So with that, let's begin. Thanks.
All right, thanks, Dimitri. Can everybody hear me from the back? All right, well, thank you, and thanks to the Physics Colloquium Committee for inviting me. I'd like to talk about the sun's corona, right? Though there will be plenty of pretty pictures of the sun, like what you see here. This image comes from Miloslav Druckmuller, who is an accomplished eclipse photographer and image processor. A lot of interesting things that are happening in that realm. I've got my list of past and current students, collaborators, co-conspirators there. I'll be talking about some of their work going forward. So the first quarter of the talk, I think, will be an additional photo gallery of pretty pictures from the sun and the corona. There are a lot of there is a lot of nice imagery to see there. But I do want to spend most of the time talking about the physics of it. There is an ongoing coronal heating problem, right? How is the corona heated up to the temperatures that we observe it to be? We'll talk about sort of the energy supply to the corona, and then how is it actually happening? And some of these questions are answered, some of them are not, and we can talk about the ongoing research. And yeah, so I do want to spend most of my time on trying to think through the actual physical mechanisms that are responsible for taking the heat, taking the energy from whatever initial source it comes from, and turning it into the high temperatures of the outer atmosphere. So when we think of the sun, we often think of just how it looks in visible light. This is a broadband visible light image. It's a nice crisp sphere. It's got some structure on it, like these the sunspots that have been seen since Galileo's time. Those rotate with the sun. They're sites of strong magnetic fields poking through the surface. And this is a great thing, but it's only really just the tip of the iceberg. This solar photosphere is essentially the deepest into the interior of the sun that we can see with photons, because if you go any deeper than that, the opaqueness of the solar gas, the solar plasma, just shoots up to very high values, and it's impossible to see any deeper. But you can see things that are higher up than this surface, because if you don't just look at the broadband visible light, you can, if you look at small little parts of the spectrum, specifically spectral lines, you see other things, right? Spectral lines are narrow little parts of the spectrum where the opacity is very high, so that when we're looking down to the surface, we don't see quite as deep as we do in the solar photosphere. We're seeing the higher layers, and you start to see more and more magnetically involved structures. So the sunspots are just sort of the initial points. these are images taken at different times, so the actual locations don't correspond. But the locations of the sunspots turn into these more extended, wispy regions where you can actually start to see the hints of magnetically aligned structures along magnetic field lines. Above the surface, you can see plasma that's sort of ejected and hovering above the surface, the so-called solar prominences. And what we're looking at here is the so-called solar chromosphere, again, because it was initially seen in these monochromatic bands of individually colored light in either the red or the violet or other parts of the spectrum. But of course, we can look even higher up than that, and to do that traditionally, it requires waiting for a total solar eclipse. And this is just sort of a fanciful way of looking at the beginning and the end of the solar corona, right? At the source of the sun, and then of course it expands out to fill the solar system, and the parts of it that encounter the Earth's magnetosphere eventually filter themselves down to something like the aurora borealis in the northern and southern latitudes. Of course, the next total solar eclipse is going to be happening within driving distance here, right? Texas all the way up to the East Coast on April 8th. It'll be it's a good chance to really see something quite fascinating. But yeah, the solar corona just extends much further out above the surface than what you can see in visible light, in the visible light of the solar surface itself. And again, it's visible mostly during a solar eclipse because the photon emissivity that you see out here is about 10 to the 6 or 10 to the 7 or 10 to the 8 times less intense than the light you see from the solar surface itself. So you've got to block out the sun in order to see the much fainter stuff off to the side. Now this, again, is sort of how people saw these things for millennia, but it wasn't until about the 1860s that a bit more quantitative study was done. People started pointing spectrometers at the light of the corona during solar eclipses and looked at the spectrum of this faint wispy light, and they discovered some new things. They saw spectral lines that were not identifiable at the time as being due to any other known chemical element. So for a few decades in the late 1800s, there was speculation about some new element in the periodic table, which they called coronium, that might exist, but nobody quite knew what it could be. And it took until the 1930s, when quantum mechanics was starting to be worked out and people were actually predicting the wavelengths and positions of spectral lines in the spectrum for these lines to really be identified. And you can see why it was quite difficult to identify them. They represent ionized species of heavy elements like iron and nickel and calcium and a few others, but so highly ionized that this Roman numeral notation tells you essentially how many electrons have been removed. 9, 10, 11, 12, up to 14 or 15 electrons have been removed, and that can only happen in an extremely hot environment. So that tells us that the outer temperature in this outer region has to be at least 1 million degrees or even more. And throughout the 40s and 50s, additional pieces of evidence were sort of clicking together that basically allowed us to really understand that yes, the temperature really is that hot. If you can analyze this light, and by the way, these red and green structures are essentially from the red, the iron 10 and iron 14 lines in the red and green parts of the spectrum, where different structures in the solar corona have relative brightnesses that vary for those two specific lines because of slight differences in the temperature. But you can also measure the density of the gas up here by measuring the intensities quite accurately, and the radial fall off of the density can be compared with models of hydrostatic equilibrium in an atmosphere, and that also tells us that the scale height has to be consistent with the temperature of about 1 million degrees also. So this was the 40s and 50s, and of course right after that was the dawn of the space age, and when people started launching telescopes into orbit, we could measure different parts of the spectrum that you can't measure from Earth. And of course, when you look at 1 million degree plasma, the place where you really want to observe it is in the X-ray and the ultraviolet parts of the spectrum. That's where most of the emission happens, and that's where the full sort of glory of the solar corona comes out. The sunspots are these super bright active regions of knots of magnetic field. You can see magnetic loops sort of all over the place, basically representing sort of dipolar magnetic sources right under the solar surface. And the thing I want to say there, of course, by showing more of these images, is don't let anybody tell you that magnetic field lines are fictional objects. You sometimes hear that in physics classes, but you can see them. They're right there. Essentially what we're seeing are regions of space where there is a sort of a high density of plasma along one field line, but the neighboring field lines don't have as much plasma along them. So yes, it's still an indirect measurement of the magnetic field, but it still is telling you exactly what the shapes of the magnetic structures are. This image on the right, which was taken just a couple weeks ago, it was shared on social media around Valentine's Day because of this heart-shaped structure. The outermost structure is actually taken in the same visible light, broadband visible light that we see during solar eclipses as well, but this was taken with an artificial eclipse. There's an X-ray image in here, but then somebody blocked out the sun to see the much fainter light out here in a so-called coronagraph. And you can see some interesting magnetically shaped structures there too. So of course, when we're going that far above the surface, that's where we see the solar corona becoming the solar wind. And going back to the 50s, there was some theoretical prediction of this, because if you do have a hydrostatic atmosphere that with a temperature of 1,000,000 degrees or more, and it's surrounded by the interplanetary medium or the interstellar medium that's much colder and lower pressure, that means that the sun represents such a source of high gas pressure that the gas pressure gradient between the sun and the surrounding space is so high that it actually doesn't, and this is what Gene Parker suggested, it can't support a truly static atmosphere that's just sitting there like a layer cake. It's got to be continually in a state of expansion and acceleration. And this was a controversial suggestion. Nothing quite like this had been thought of before. I've got my cartoon of a balloon that's expanding because of the pressure gradient between its center and the environment in a similar way. But it only took a few years for other space missions to be launched beyond the Earth's magnetosphere to directly measure the properties of the solar wind. Marcia Neugebauer and others published this in '62 and basically confirmed the basic outlines of Parker's initial ideas. Some differences that we'll talk about, but basically proving that the solar wind really does exist. Since then, there's been a lot of other ways of measuring it. We can use telescopes now to measure it. This is now another series of images from a coronagraph. So after you block out the disk of the sun, you can see the much fainter light. Each frame of this movie has been processed using some image processing or wavelets or something in order to highlight the small differences between the bright and dark structures. And you see that there's continuously an outflow everywhere, right? If you were to play this movie in reverse, you would see things going in, right? It's not just random noise. You're actually seeing the outflow of various structures in the solar wind. The plot here just shows 1 year's worth of measurements from a spacecraft at 1 astronomical unit right around the orbit of the Earth, showing that the solar wind speed varies in a relatively narrow range between about 300 and 700 kilometers per second. It's kind of a bimodal distribution that you can sometimes see between the slow and the fast solar wind. And yeah, studying the properties of the solar wind is a whole other subfield. I don't know how much time I'll get to talk about it. I do want to talk about the physics and to really talk about the plausibility of there being a corona. We want to think about how much energy is actually available to provide the heat to the corona. Because again, it seems strange that the core of the sun has a temperature of millions of degrees, 15 million degrees or so. That drops off to about only 6,000 degrees at the surface. And now we're saying that there's this superheated layer above where it heats up again to 1,000,000 years. Something's got to be providing that energy in a continuous way to heat it up. Now, I can quantify that a little bit more by showing you actually what we believe the temperature as a function of height above the surface is doing. If there was no coronal heating, this surface temperature of 6,000 degrees would just drop off relatively slowly as a function of height. I think this is so-called the radiative equilibrium solution for the temperature. But we see it jump up in kind of a complicated way. There's this initial period of heating that we call the solar chromosphere. That corresponds to those multicolor regions that we saw in the visible spectrum. And then there's this rapid jump up to 1,000,000 degrees, yes. And then the solar wind kicks in further above. I don't want to overstate the mysteries, right? There are a lot of unanswered questions, but there are some things we do understand pretty well. And I do want to highlight those because, there are successes in terms of understanding things so far. And this also relates to a topic from last month's physics colloquium from Scott Parker, who talked about fusion plasmas. And this rapid jump from temperatures of about 10,000 to about 1,000,000 degrees is exactly the same topic that he talked about last month that he called burn through. Essentially, as you're heating up a plasma, and he was talking about tokamak plasmas or fusion plasmas in the laboratory, there are these temperatures of about 10,000 degrees where most of the atoms and ions still have some bound electrons on them. Those bound electrons can get excited and drop back down in energy levels and produce photon radiation, and those photons can actually cool down the plasma to a degree that keeps the temperature stabilized at this temperature of about 10,000 degrees. However, if you keep heating it and you keep decreasing the density, which happens as you go up higher and higher above the solar surface, there reaches a point where the plasma ionizes pretty much completely. There are no more bound energy levels, no more spectral lines to take the radiation to cool it back down again. So there's this catastrophic instability where it just rapidly heats to the next sort of stage of a stable solution to the thermal energy equations, and that's a temperature of about 1,000,000 degrees. So this rapid change is something that we think we understand, and we see it in laboratory plasmas pretty reliably. It's how, where does all this energy come from in the main part of the corona? The other thing that we do understand pretty well, as I mentioned, was Gene Parker's, different than the other Parker, model of the gas pressure gradients generating the solar wind. That initial model, I think, does pretty well. It gives us an answer for the solar wind speed within about a factor of 2 of what we actually see. So that, I think, I would call a success and one understood part of the entire problem. We still want to do better than that factor of 2, though, because we do want to do more accurate space weather forecasting, which I'll talk about a little bit later, and we want to really understand how individual parts of the solar wind are accelerated, even when Parker's mechanism might not be the entire story. But it's a good part of the story. All right, so then the question, where does the heating actually come from? So I'm going to take you on a journey, I guess, from the interior to the sun to the exterior, and we're going to be following the energy flux of a certain type of energy that starts off in the convection zone of the sun. Right? Beneath the sun's surface is a roiling, boiling plasma where there are hot blobs that are rising because they're buoyant and cool blobs that are falling because they're heavier than their surroundings. And that overall process transports the photon energy of the sun out through this so-called convection zone. Near the surface, the actual magnitude of that energy flux is something like 63,000 kilowatts per meter squared. And I'm just going to keep using that same set of units because we'll see how that filters out through the corona as well. So that's happening in the interior. When we get to the surface, the convection stops, right? Just like at the top of a boiling water, there's not convection happening above the top. But as we look down to the surface, we can actually see the tops of the convection cells. This is an actual movie of a small little piece of the solar photosphere, and it looks like a pot of boiling water. We're seeing the hot blobs rise and the cool parts, the dark lanes in between the cells, fall back down. But it's not actively convective at this point. So there's really only a small remnant of this energy flux at the surface. If you measure the motions at the surface, the local kinetic energy flux is only about 500 kilowatts per meter squared. So it's a big reduction from what's happening in the interior, but it's still a good number that seems to be available for conversion into other forms of energy as you go up from the base of the corona. Well, then the question is, how much of that 500 kilowatts per meter squared actually makes it up to the corona? The next time I click my laptop, I'm going to show you a picture on this that I've been warned against showing people in talks like this. It's been called a confusogram, and I'm warning you in advance. It'll be kind of nasty. But when we actually think about how the magnetic field is connected from the interior to the surface to the chromosphere to the corona of the sun, it's a complex and chaotic and stochastic environment. And when people try to make cartoons that simplify things, well, in this case, this is about as simple as they could make it. And yeah, this was made by Sven Vedermeyer. It's called his confusogram. And really the vertical direction here is height above the solar surface. These little arcs down here are the convective bubbles. There are many different scales. There's the granulation, the supergranulation, all sorts of convective motions at the surface. And most of the solid curves here represent magnetic field lines that are poking through the surface of the sun and extend up into the corona. The big takeaway that I want to have you take from this is that if you're looking up here in the corona and you look at a typical sort of volume of gas in the corona, and you want to know how is that magnetically connected to what's happening down below at the surface, it turns out that only a small fraction of the solar surface is connected up to the corona. Many of these other regions just never seem to have any sort of causal connection to what's happening in the corona. It's a simplified way of saying it, but it's a complicated situation, as you can see from that. But the takeaway is that only something like 1 to 10% of the photosphere is magnetically connected to the upper atmosphere. So if you really want to talk about the power per unit area that's available to the corona, it's only going to be 1 to 10% of that 500. So 5 to 50 kilowatts per meter squared. There's a lot of interesting physics in that 5 to 50 kilowatts per meter squared. I can highlight one bit of it that is that the magnetic field lines that are poking up through the surface are jostled by the convection. That convection is always moving and roiling and boiling, and those magnetic field lines are jostled in a bunch of ways. The traditional way of studying that is to just mainly look at the transverse motions of those flux elements, essentially as they sort of random walk their way around the sun. That provides some kinetic energy flux. Sam Van Kooten, a recent graduate, now a postdoc at Southwest Research Institute, did some additional analysis of this and found that as we're going to get better and better images of these magnetic structures from the NSO's DKIST telescope, the big 4-meter telescope on Maui, we're going to need to do better than just looking at the transverse random walk motions. We're going to need to examine the shape changes of these bundles of magnetic flux. Not just the fact that they can get larger and smaller in area, the so-called sausage modes of magnetic flux tubes, but also the fact that they can change their shapes in a whole range of different ways to basically create these very non-circular cross-sections. And if you look at the energy flux that can be carried up in those other ways, they pretty much compare at the same order of magnitude with the traditional random walk energy fluxes. And you can see that you get things in the order of 20s, 30s, 50s maybe kilowatts per meter squared. So you really need to take account of the magnetic geometry and topology of these structures as you're following them up into the corona. So what do? We need to figure out how this 5 to 50 kilowatts per meter squared makes its way out. I'm showing two other collaborators here, Momchil Molnar, who's another postdoc at HAO, looks at the solar chromosphere and tries to measure these fluxes. Masha Kazachenko here at CU looks at it as a more magnetic problem, looking at the pointing fluxes of magnetic field that's transmitting energy up through the photosphere, and they sort of measure the parameters of this 5 to 50. But for coronal heating, we want to know, how do things keep happening? What fraction of that 5 to 50 is actually available for particle heating? it can't be 100% because we do know that as these magnetic waves come up from the surface of the sun, some of that energy keeps going. Some of that energy keeps going out through the solar system. We measure waves and turbulence pretty much everywhere we look out in the solar system. So some of it survives, but only a fraction of it gets converted to heat, essentially converted to the random motions of the individual particles. But the big question is this, do we really have a problem? And it turns out that the energy that's required to heat the corona up to its observed temperature is really just of the same order of magnitude, or maybe a little bit less than what we actually have available. That's good news, I think. That means that we're not missing any big chunks of energy in the solar atmosphere. It means that the actual source of the energy for coronal heating is pretty well accounted for. And I'll talk a little bit more later about how we actually determine this. But for now, the big question is, how does it actually happen, right? I skipped something in the middle, and many of you know the old Sidney Harris cartoon of then a miracle occurs, and you really need to be more explicit in that second step. And that's really where I want the rest of this talk to go, to talk about how it actually happens. How does the heat actually go from this kinetic energy of the random motions into the particles to create higher temperatures? So to do that, I want to just define a couple of terms, a couple of time scales in the system. These time scales are basically just defined as typical length scales divided by typical velocities. That just has units of time. And we can talk about time scales for the photosphere. Basically, what is the time for these kinetic energy motions, the remnants of the convection, to move things around on the surface? I'll call that the photospheric correlation time. And then what's the time scale that I'm calling TA or T alphane? What's the time for for perturbations in the magnetic field to propagate along the magnetic field through the corona? So it's basically comparing the time it takes for the base driving, how fast is that happening, to the time it takes for information to propagate along those magnetic field lines above the surface. And when you see two time scales, the typical thing you often do is figure out what happens when one is much bigger or much smaller than the other. So if you take the one extreme, where the driving time scale is very fast, but then it takes time for information to propagate along the magnetic field, you can almost think of it as plucking a guitar string and then watching the wave propagate along the guitar string. This is, as I just mentioned the word wave, this is the realm of waves, right? You can watch these waves propagate along the magnetic field. There are observations of this. And the heating occurs because a wave propagating through a system isn't always just a simple harmonic oscillator. Sometimes it's a damped harmonic oscillator, right? You've solved those kinds of problems. And when there is damping in the system, specifically in this case by particle-particle collisions, things like viscosity, friction, magnetic resistivity, other types of effects like that, the ordered motion of the wave damps out over time. And much like from friction, where does that energy go? It goes into heating up the system. That's where the heat comes from in models like this. They're often called AC or alternating current systems because the focus is on how do the waves evolve over time. Then there's the other extreme, right? What if the driving at the base was very slow, but the time it takes for information to propagate along the field was very rapid? This cartoon over here is essentially the same cartoon here, but I've taken a scissors and cut these two ends of the magnetic loop and put one over the other just to emphasize what the magnetic field ends up looking like in this opposite extreme. Because if it takes no time at all for the field to respond to these slow random walk motions at both of the foot points of the field, then the magnetic field is going to undergo is essentially going to always be in a state of equilibrium, because the time it takes for waves to propagate and to convey information through the system is going to happen in an instant, but it's still always going to remember the past history of those slow motions. So over time, the magnetic field will become more tangled and braided and twisted as is illustrated here. And there are places where it's even more tangled and braided and twisted than other places. And in plasma physics, when you have magnetic fields of opposite polarities, or at least some component of opposite polarities, that come into close proximity with one another, this is when this phenomenon of magnetic reconnection happens. It's a very bursty and stochastic release of energy. The magnetic energy at this null point where the fields cancel out, the magnetic energy is converted violently into heat and radiation. There are things called solar flares that happen at these regions, and in the solar corona along a typical loop, these flares might be small little sparks of heat. And in this type of model, these are called nanoflare-driven coronal heating models. That's where the heat comes from. But because of the slow foot point driving, these are called DC or direct current models. These are sort of the two notional extremes that you have to think about for the corona. Unfortunately, in the solar atmosphere, we're not in that situation. When you measure the different time scales, they're always within maybe about a factor of 10 of one another. So the situation is neither purely AC nor purely DC. It's some sort of messy combination of the two. So when we talk about models, this is just another slide of different types of models. And the first two are essentially just recaps of the AC and the DC models. It's really going to be some hybrid of the two. But that's not even all, because there are some other ideas. And I just want to quickly summarize those. And essentially, the one on the lower left takes into account the fact that the magnetic field that we see at the surface of the sun isn't just sitting there being jostled around. The solar dynamo in the interior is continuously generating new magnetic field. Those magnetic field lines are buoyant and they float up through the interior until they poke through the surface. There is emerging magnetic field from underneath the surface all the time. And sometimes when those emerging magnetic fields interact with the magnetic fields that are already there, again, you can have, look at the arrows. If you have oppositely directed fields that are pushed into each other, you can have forced magnetic reconnection that changes the magnetic topology, creates violent heating events, sometimes can create outflows called coronal jets that we can also observe. So this can happen too. This is called interchange reconnection, because the actual conductivity of the field shifts when the field annihilates itself at certain points. There's also this other idea that happens in the regions above sunspots, where the magnetic fields are very strong and become gradually twisted, essentially similar to the magnetic fields in fusion tokamaks. There is an axial component of the field and a poloidal component. It's a twisted helical magnetic field. And those types of magnetic fields contain a lot of magnetic energy, and that extra magnetic energy sort of wants to relax down to a lower energy state, and there's all sorts of ways that have been suggested for them to relax back down to that lower energy state. And when the magnetic energy goes down, that usually goes into heating for the particles as well. There's all these different ideas for where the heat can actually come from, some of which involve magnetic reconnection on different scales, but some which don't. And of course, in the last couple decades, the thing that people have tried, of course, is let's just put all this stuff into a big computer simulation and see what happens. And that has been a successful realm of activity. I've just got a bunch of snapshots, and I'm now just realizing that I think even the most recent of these is at least 5 years old now. So there's probably much better higher resolution simulations out there. I still don't think those simulations are resolving all of the important scales in the system. There's still many, many orders of magnitude of spatial scales and time scales that can't be represented in these numerical simulations. But they generally do a good job of producing some kind of coronal heating. So this is a promising avenue for the future. If we can ever get to the point of resolving all the scales, that can answer the questions. We're not there yet, because right now the fact that we don't resolve all the scales, I think, has weighted the actual processes that give rise to the coronal heating towards one end of the spectrum. I think these are more DC than AC, because we really can't represent, we can't represent all the structures of the waves that we know must be present in these systems, in these computational boxes. But it's a good start. So before I move on to the solar wind, I just wanted to talk about a couple of interesting new and old wrinkles on the problem. One of these is to try to take seriously this very sharp transition region from the chromosphere to the corona. It's very, very thin. It's maybe 10 or 20 kilometers thick, whereas the solar radius is 800,000 kilometers or something. And so this is something that's definitely not resolved in these 3D simulations. A paper that just came out last year with Momchil Molnar worked out some of the consequences of what happens to the waves in the vicinity of this sharp transition. Let me ask some of the students in the audience, what happens to waves when they encounter a sharp boundary between two different types of media? Anybody taking E&M? What happens? Some reflect and some refract, yes. And in a plasma, that happens, and it happens in an even more complicated way. Because if you have, there are multiple types of magnetohydrodynamic waves that can exist in a plasma, and if you start with just one of these waves that encounter the sharp boundary in a generic case of a generic geometry and an arbitrarily oriented magnetic field, what comes out is not just one reflected and one refracted wave, but three of each. Essentially, it generates all three types of alphanic, slow, and fast mode magnetosonic waves, the three types of waves that can exist in MHD that are transmitted and are reflected. It's a complicated system. We studied this for conditions close to the realistic solar transition region between the chromosphere and the corona, and it turns out that many of these waves damp very rapidly right in the vicinity of this boundary, and that produces a localized little bump of extra heating right at that boundary that I don't think has been included in other models and simulations. So there's still some interesting things to learn from more restricted analytic and semi-analytic models as well. Another interesting bit of math is what I'll call an old wrinkle. Remember I said that the energy required to heat the corona to its observed temperature was a certain value. Well, how do we actually know this? This comes from a whole different sort of field of modeling that I'll call physics agnostic modeling. Essentially, if you just assume that a certain amount of heating exists, you can follow the thermodynamics and figure out how hot the corona should be, how dense it should be. This was done starting with Rosner and colleagues in the 1970s. And I think it's an interesting math problem, or a math physics problem, because essentially what it is a time-steady version of the first law of thermodynamics, right? How much, if you put in some heat, what is the response of the internal energy of the system? It's an interesting second-order differential equation. And I've just given a simple example of it here. And it's a second-order, nonlinear, because it involves the radiation due to the burn-through at the colder temperatures, which is a nonlinear function of temperature. But it's interesting because it's an overdetermined system. This is an interesting trick that I don't know if they teach you in some of these math physics courses. So it's a second-order differential equation, and for a second-order equation, you normally have two boundary conditions. The question is, if you look at the physics of the boundaries here, it turns out, and Rosner and Tucker and Viana looked at this, there's actually 4 boundary conditions that you can realistically specify. That overdetermines the system. But what it also does is allow you to calculate these other constants that I've called alpha and beta in the system. They kind of act like eigenvalues of this problem. And this alpha and beta are dependent on some things that we actually don't know going into the problem. What is the peak temperature at the top of the loop? What is the pressure at the base of the loop? And it's interesting because it's not just solving a boundary value problem. It's a nonlinear eigenvalue type problem that is kind of fascinating. And I'll just point to some recent work that over the past decade or so that Avery Schiff, another past grad student, worked on various sort of more complicated versions of this. There are some cases where the temperature does not peak at the apex of the loop. It peaks sort of halfway down, and then there's a local minimum at the top of the loop. There's also, if you assume this is not a coronal loop, but something that goes out into the solar wind, the open boundary conditions at infinity become an interesting, a different way of mathematically looking at this as well. I can give more details about some of this if anybody's curious. But yeah, I just wanted to point to some of the more sort of paper and pencil approaches that you can take to some of this that complement the results of high-powered computations. All right, final part of the talk is the solar wind, right? So how is the solar wind accelerated? I answered that in part by talking about Gene Parker's idea. If it's hot, there's a high gas pressure that keeps an acceleration going. But the big thing that we've learned as we've measured the temperature at various places in the solar wind is that it's not enough to just heat the corona and then stop at some point and then just let the solar wind go. There has to be extended heating all the way out, pretty much all the way through the solar system. So I can show you a sort of a summary of measurements of temperature as a function of distance above the solar surface. And this x-axis in log space really goes over many orders of magnitude. Right? There's just fractions of a solar radius down here. Here we're 1 solar radius above the surface, 10, 100, 1,000. Right? The orbit of the Earth is out here at 215. So we're looking at in situ space-based measurements of particle temperatures from both inner heliosphere missions like Helios and Parker Solar Probe, and outer heliosphere, things that go all the way out to Voyager. And we've got telescope estimates and inferences of temperatures in here. I've got red and blue for separate measurements of the protons and the electrons, because this is a plasma that has a very low density as you go out, and a low density plasma becomes collisionless. So the different components of the plasma, say if it's just hydrogen, the ionized components are going to be the protons and the electrons. They can have different properties. If there aren't frequent collisions of the particles that keep them in a common thermal equilibrium, they can go out of thermal equilibrium. The protons can be 2 or 3 times hotter than the electrons for some reason that we still don't understand. But the reason I wanted to show you this was that if you heated the corona only up to about the tops of the loops that you actually see, that extend for about 1 solar radius above the surface, and then let it go, what you would really get is a temperature that dropped off like the green curve, and that is much colder and much steeper declining as a function of radius than what we actually see. So it is actually the case that extended heating gradually throughout the solar wind is something that's desperately needed in order to explain what we actually see. It's a slightly different realm than the heating of just the basal corona. So there's been a lot of work over the decades on this as well, and I think that there's been a lot of success in sort of a unified AC and DC picture of waves and nanoflares that is often talked about under the umbrella of magnetohydrodynamic turbulence. Essentially, turbulence is a chaotic set of motions that cannot be easily decomposed into waves, and it's also evolving in a way that's faster than the DC picture that I talked about before, but it involves a lot of the same physics. So we've got the surface of the sun where the convection is shaking the magnetic field. Those shakes are like plucking a guitar string. They propagate up the field into the solar wind as so-called Alfvén waves. And as we're going out into the solar wind, the background properties of the solar wind are changing, right? The density is high near the sun. It's low out here. So it's almost like a gradual version of that sharp wall that we just talked about, right? If you have a wall, you can have some reflection and some transmission. But if you make the wall smoother and smoother into a gradual change, you'll have gradual partial reflection of some of these waves coming back down towards the sun. We observe that, and we see that happens. If anybody's taken a plasma physics class, you'll know what happens when you have Alfvénic wave packets that are counter-propagating along a magnetic field line. When those packets collide with one another, that's when they can really break up into a more chaotic or stochastic type of turbulent motions. I can just show you sort of a cartoon picture of what the cross sections of those field lines look like when they crash into one another. They spontaneously shred themselves into these more and more chaotic scales. This is another sort of a snapshot of a simulation that shows what's happening along these magnetic fields. You can't even really see, you cannot even really see separate upflows or downflows in a thing like this. It's just the counterpropagating structures that are interacting with one another to produce this turbulence. And as the turbulent shreds get smaller and smaller, there eventually turn out to be counter-oriented magnetic field lines. And when they get pushed together, you get this magnetic reconnection. And on the smallest scales of these types of models, you get little sparks of heating, and the heating comes out as these little nanoflares. So this is sort of a hybrid, as I say, a hybrid between the wave AC picture and the nanoflare or DC picture. And it's been kind of successful. It's been studied since the 80s, and it is now an ingredient in some numerical simulations that include the solar wind. For example, this is a simulation from Zoran Mikic and colleagues at Predictive Sciences in San Diego, I think, and they do these global models of the corona and the solar wind to help in space weather forecasting and also to predict the appearance of future solar eclipses. I think this was produced a month or two before the 2017 solar eclipse, and they would then compare it to, I forget, and they're showing the sun rotate here, and I think at some point you can actually see where the day of the eclipse is, because it's a very familiar shape if you've seen pictures of that eclipse, and it's a very successful thing. They put in this MHD turbulence as the heating ingredient in these simulations, and it works pretty well. There's also more focused simulations. For example, if you don't want to do it globally and you just want to look at a little wedge of the solar wind, you can look at a more detailed simulation and follow the individual turbulent fluctuations as they flow out and get partially reflected, and all these things that I talked about happen in a pretty self-consistent way, and the amount of heating and the amount of acceleration that gets produced is very close to what we actually see. So yeah, I think it's overall been a quite successful thing. Still can't quite say that we've solved the problem though, because if we really want to solve the problem, we can't just provide one possible answer and show that it agrees with the observations. We also have to take all those other ideas and show that they don't work, right? You really want to try to boil it down to one unique answer, and we haven't done that. There's been a lot of work on this turbulence idea. It's plausible, it does a lot of the right things, but we still need to take some of those other ideas and take them to the point where you can compute these same things. So yeah, we're getting there. And testing these models really also requires comparisons with data, because if two models produce the same simulated observations, that just means that we haven't chosen the right observations yet. We want to find the right types of data that help us distinguish between the models and not just where they both work. So I just have a few, ongoing and future types of observations. Parker Solar Probe, I'm sure many of you have heard of, was launched in 2018 and is the spacecraft that is getting the closest to the sun from any other mission. Next year, it'll reach its closest approach to the sun at 9.8 solar radii from the, I think that's from the center of the sun, not even from the surface. And it's revealed a lot of interesting dynamics that we haven't been able to view from spacecraft at 1 astronomical unit. And the modeling is starting to incorporate the insights that we've gotten from this new view of the inner solar wind. Now the telescope missions are progressing as well. There's this mission called PUNCH that Southwest Research Institute is working on. The polarimeter to unify the corona and the heliosphere is essentially a set of 4 spacecraft that will produce mosaic models, mosaic images and movies of the white light. It's essentially this coronagraph concept where you block out the sun and you look at the white light. But this will have a huge dynamic range from 5 to 150 solar radii. It's essentially going to reproduce and do much better than these wavelet type movies from other coronagraphs. And it'll have, an image every few minutes or something. So it'll eventually have petabytes of data that it'll send down. and really help us map out the acceleration of the solar wind in great detail. Yeah, I have other wish lists of other things I'd like to have funded and send up there, like more of this ultraviolet spectroscopy that can help us reveal these collisionless effects, right? The differences between the proton and the electron temperatures. There's a lot more gold in those hills, I think, especially when looking at the heavy ions in the solar wind, where we have hints that they're much hotter than even the protons and the electrons combined. Yeah, so a lot of interesting ways forward. The final topic I do want to talk about sort of the what practical use we can put all of this science to, right? Forecasting space weather is an important practical use. You know, all this time variability in the solar wind that encounters the Earth's magnetosphere and perturbs it can produce a lot of detrimental effects on technology and people, right? Astronauts, even high altitude airline crews need to know the state of space weather to see how much of a radiation dose they might get, especially if it's a polar flight over the North Pole. Boulder is a big home to this. We've got the Space Weather Prediction Center from NOAA here in town, and CU just recently inaugurated a new center of excellence from NASA called the SWORD Center. It's mostly based in the Aerospace Engineering Department. Very sort of practical way of looking at the impacts of varying space weather. The connection, I think, comes from going beyond empirical correlations. There's plenty of correlations out there, and they're used for space weather forecasting. Right? They're often of the form, when the sun's magnetic field looks like this, the wind speed that we encounter at the Earth is that. That's nice, it works, but we want to do better. We want more accuracy in these forecasts, and we want to extend their lead time to longer times so that we can be better prepared for these things when they're coming. To do that, we really need to understand the underlying physics. I've got this obligatory XKCD cartoon about correlation versus causation, but yeah, we want to do better. We really want the causation and not just the correlation for doing this. I think that's about all I have. On my conclusions, I'm really just saying, yeah, although these problems are not solved, I think we're doing better and better. We're putting in more and more real physics in these models. They're doing better at explaining what we see. A lot of this has been aided in a very interdisciplinary way. It's not just solar physics. There's plasma physics, laboratory, space physics, instrument building, astrophysics, because there are other stars than just the sun, too. We can measure their properties. Engineering, of course, and a lot of this observational validation. This is just a smorgasbord of current, past, a few recent past and future missions, and I could talk about any more of them. But before I end, I just want to, instead of ending on this slide, I'm going to end on another slide with some references to a seminar course where everything's on YouTube, and a review paper, and pointers to all the other students I've worked with that I haven't had a chance to mention their work, and highlighting them as well. So thank you.
Thank you very much, Steve, for the great talk. Let's see if there are any questions from the audience. Right, okay, there are some questions. Maybe
yeah,
I'll...
So,
you can just shout, yeah.
Yeah, so towards the end of the talk, you emphasized the desire for a single explanation, right? Like one heating mechanism to rule them all, right? And is there any reason to believe that? Because like active reading coronae seems to me as a non-corona person to be a very different beast from my corona. And so why wouldn't we expect a different heating mechanism to be on there?
Yeah, no, great question. Should I repeat it just for the
just in
recording?
case, yes.
Yeah, the question is it really just going to be one mechanism to rule them all, or will it be a combination of different mechanisms for different parts of the corona or different parts of the solar wind? I do think it's going to be the latter, and the quantification of that is going to be a challenge, right? What we really want is what are the relative contributions of these different physical processes for different regions. Yeah, we can't say we've solved the problem until we really know those relative contributions. There are some interesting Bayesian hypothesis testing papers out there that sort of point the way towards quantifying that. But I think to do that, you really need to have a full set of complete options to choose from, right? And I don't know if we're there yet.
Other questions? Thank you, Steve.
Just a little curiosity of mine. Does the temperature of the corona seem to have any connection with the solar cycle? So do we see any additional warming during a solar maximum?
Yeah, it's mainly, the question is, does the temperature of the solar corona have a correlation with the solar cycle? Yes, and the intermediary there is the solar magnetic field, the coronal magnetic field. Early on I showed this picture with the red and the green from the visible light, and it shows that the closed magnetic regions and the open magnetic regions some have slightly different relative amounts of these different lines. That is directly proportional to the relative temperatures. And at solar maximum, there are more of these closed active region parts. At solar minimum, it's much more of like a dipole, where the open parts are at the north and south, and there's sort of one big loop in the equatorial regions. So yeah, so the regions that vary with the magnetic field definitely take with it different amounts of coronal heating. Yeah.
Thank you.
All right, so I should first say that I'm not a solar person. I'm a turbulence person from the hydrodynamics community, and I'm here because you had the word turbulence in the title of your talk. So I want to understand the turbulence. So if I'm understanding the mechanism correctly, why the corona is heated high, but also why the temperature stays high. It doesn't drop down as it should if there were no additional sources of energy, of thermal energy, to maintain that high temperature. If I'm understanding the argument that you gave, it's because of these magnetic waves propagating out, but they have to convert into thermal energy, and that conversion process involves basically a turbulence-like mechanism that they break down. But the explanation was that they reflect back so that you get traveling waves going opposite directions, and that there's some interaction between them that leads to a cascade to smaller scales like turbulence does, and eventually into the thermal scales. Did I get that right?
Yes. This counter-propagating or partially reflected turbulence is basically a wrinkle on Krichnan's idea of counter-propagating Alfvén wave packets.
Right.
That shred and cascade.
Right.
One thing I didn't mention about the discrepancy between that green no heating curve and the actual observed curve is that there is also heat conduction. Right. There's also conductivity that helps keep the temperature higher for longer. That's sort of built into these heating models as well.
And that's a significant contributor to maintaining the temperature up rather than coming down like...
in the inner corona for sure, but as we get out to the collisionless outer corona, there is a lot of active work in figuring out what does heat conduction look like when you've gone collisionless. Right? Because maintaining the skewness in the particle distribution
conduction
often
requires collision, doesn't it?
Like Chapman-Enskog theory, it requires collisions.
Conduction requires collision,
Yeah.
right? That's the nature of conduction.
Right, but there are some collisionless extensions of heat conduction
Really?
as well.
Okay. All right. So I have more questions, but other people do as well.
So let's see, there is a question over here.
Okay. At the beginning of the talk, you mentioned two timescales, photospheric and Alfvénic, and they're similar, well, within a factor of 10. My question is, what happens when they're identical? Then you would get resonances, and resonances are a very efficient way of transporting heat, energy, etc. Any comments on that?
There is a whole subfield of coronal loop heating specifically where these resonances are taken into account. When those models are compared to the 3D simulations, I think it's been hard to find them. I think most of the natural response of the corona in a frequency domain is very broadband. So I don't think specific heating on certain resonances is ever a dominant thing, but it can be there certainly.
Thank you. Are there any other questions? Oh, okay.
Well, I guess you do because of the recording. So why is it that the radiative transfer, which is orders of magnitude higher than the transfer that you were describing, you were like 10, the units kilowatts per meter squared versus 60,000 or something like that? 63,000 I wrote down here kilowatt. Why is that 63,000 kilowatt per meter squared going? Why isn't it heating?
That, I mean, by the time that's what's being carried by the active, unstable convection beneath the surface. And when that's carrying essentially the solar luminosity up through the surface. When you reach the surface, most of that is actually transferred back to photons to make the solar luminosity what we see in terms of watts.
Right. So it just keeps
being-
going.
It keeps
doesn't-
going mostly as
It
photons.
doesn't heat anything.
Right.
Okay,
It's
got
just
it.
that small fraction that remains kinetic energy.
Thank you. Great questions. Great discussion. Well, if there are no more questions, let us thank Stephen again